Okay, 8.3 is going to cover dilations. Now, a lot of this section is review from our similarity unit because really a dilation is a size change which makes similar figures. So we are going to blow up or shrink a figure proportionately. And that is the key, because we are going to change it all the same. We're going to increase it all by a factor of 2, or we're going to shrink it all by a factor of 1/3. So everything's going to same. We are going to essentially make similar figures. So a dilation creates similar figures, where the other transformations made congruent figures. And if you remember back to that similarity unit, we talked about the scale factor. We talked about K. And so our rule for every size change, every dilation, is going to be take your original x, y, and your image point will become K times x and K times y, where K is your scale factor. Now, formally, we're going to talk about a center of dilation, just like we talk about a center of rotation. But for us at this level, our center of dilation will always be the origin, 0, 0. In later courses, we can move the center off of 0, 0. But for us, for now, the center is at 0, 0. So really, this section is as straightforward as it seems. How do I move from the pink triangle to the blue triangle? What changes? Well, remember we talked about K could always be found by taking new over old, by taking our image, size, length, coordinate over our pre-image. And so by looking at these, we can pretty quickly see, just by comparing these coordinates, how we got from A to A prime, B to B prime, C to C prime. But if we want to look at it formally, we could take the A coordinate and compare it to the A prime coordinate. And what we would find is that K would be equal to -4 over 2, -2, which is 2. And if you look at all of those coordinates, that does indeed work. Now, if we were to look at the length of AC, we could do the distance formula and find the length of AC. So the distance of A to C is the square root of -2 minus 0, the quantity squared, plus -2 minus 2, the quantity squared. So we have the square root of -2 squared plus -4 squared. Careful with your negatives. So the square root of 4 plus 16, which is the square root of 20. Use your simplifying, 2 radical 5. If I do the distance from A prime to C prime, we would expect it to be 2 times bigger because everything is getting 2 times bigger. So let's see if that happens. So I'm going to take -4 minus 0, the quantity squared, plus -4 minus 4, the quantity squared. So I've got -4 squared plus -8 squared, which means I have 16 plus 64, which gives me the square root of 80. Work your simplifying. The square root of 80 is 16 times 5, which is 4 square roots of 5. And so you can see that A prime C prime is equal to 2 times AC, because 4 square roots of 5 is equal to 2 times 2 square roots of 5. And so you just verified the property that the distance is twice as big, which means when we think about preserving ABCDO, we're really talking about angle measure between its collinearity and orientation. Notice A, C, B, A prime, B prime, C prime. Orientation is preserved. Those are all preserved. But distance is not preserved, as you would expect if we are making things bigger and smaller. So a couple of quick, straightforward examples. If the polygon RTGH has these vertices and it undergoes a dilation with a scale factor of 3, what are the new coordinates? So our rule is really saying all of our new points will be 3 times the x-coordinate and 3 times the y-coordinate. And so being careful with your signs, r prime is negative 12, 1. T prime is 6, 9. G prime is 6, negative 3. And H prime is negative 12, negative 9. Now, if we are going to graph ABCD with the following vertices, A, B, C, and D, and then perform a dilation with a scale factor of 1/3, graph the new image. Now, remember, little side note, K is greater than 1, my figure is going to get bigger. K between 0 and 1, my figure is going to get smaller. So I expect when I'm graphing this, my figure should get smaller. So my original A, B, C, D, is right there. If I go through and think about the scale factor, remember multiplying by 1/3 is the same as dividing by 3. And so A prime is going to be at negative 2, 2. B prime is at negative 2, negative 2. C prime is at 2, negative 2. And D prime is at 2, 2. When you graph that, and remember to always label your coordinates, my new one is 1/3 as small. And if you check your distances and your lengths, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1/3 of 12 is 4. 1, 2, 3, 4. And it works out exactly as we expect it should. Now that brings up a review type problem. Now, in the similarity unit, we talked about how surface area and volume were related to size changed figures. And if you remember, one dimension, so talking length and perimeter, varied by a factor of k. It got k bigger or k smaller. If we had a two-dimensional measurement, like area, that varied by a factor of k squared. And if we have a three-dimensional figure like volume, measurement like volume, that was going to vary by a factor of k cubed. And we could run through these and look at them as examples of how this works. I'm going to show you this time about kind of how to use this k squared. So our original. So we need to know our original surface area is 2 times 10 times 5 plus 2 times 5 times 4 plus 2 times 4 times 10. And that is 220 units squared. That tells me two dimensions are going to vary by a factor of k squared. Volume is base times height times length. So I have 10 times 5 times 4, which is 200 units cubed. That's my old figure. Now, in A, my new figure, k is 2. So All of the lengths are twice as big, so obviously this would be 10, or 20 rather, 10, and 8. And we could go through and do the formula. But what happens, because we know the original, is we can say that the surface area of my original times k squared is my surface area of my new. And so we can say 220 times 4 is 880 units squared. And if you work out the formula, you will get the same answer. And if we use the same idea to say the volume of my original times k cubed will equal the volume of my new picture. And so I have 200 times 2 cubed, which is 8, for 1,600 units cubed. And again, if you take 20 times 10 times 8, you will get 1,600. Shortcuts. Understanding scale factor is a shortcut. So in this next example of B, k is 1/4. So things get a slightly messier. So instead of having 10, we would actually have 10/4, which is 5 halves. We would have 5/4, and we would have 1. So you could go through and use the formula. You're going to end up with some yucky fractions. But if I say that the surface area of my original times k squared is the surface area of my new figure, then I get 220 times 1/4 squared, which is 220 over 16, which reduces to 55 over 4. And you're done. You can repeat the same thing with the volume of my original times k cubed to get the volume of your new. So I have my volume of my original was 200 times k cubed is going to be 200 over 64, which reduces. So 20 over 64 reduces to 25 over 8. So knowing that k squared, k cubed relationship allows you to take a shortcut to finding the value of volume, surface area, finding the scale factor, etc. So the key and the pattern is really this up here, and remembering how we utilize that. So if I give you two volumes compared, you can take the cube root, which is k, square it to find surface area. That's the sort of thing that's on the end of the homework, which is review from our similarity unit. So good luck with your homework, and quiz